These are the answers to the AP Chemistry packet on topics 1.7 to 1.8. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. Question 1 says, based on periodic trends and the data in the table above, which of the following are the most probable values of the atomic radius and the first ionization energy for potassium, respectively? So we are given a table in which the atomic radius of calcium is given as 194 picometers, and the first ionization energy for calcium is 590 kilojoules per mole. So we have to decide if the atomic radius for potassium is larger or smaller than 194 picometers, and if the first ionization energy for potassium is less than or greater than 590 kilojoules per mole. First, let's take a look at the trend for atomic radius on the periodic table. So the trend for atomic radius is that atomic radius decreases from left to right across a period, and atomic radius increases from top to bottom down a group. So there are potassium and calcium. They are located in the same period, and since atomic radius decreases from left to right across a period, we expect the atomic radius of potassium to be greater than that of calcium. So for potassium's atomic radius, it should be larger than 194 picometers. So the correct answer is either A or B, since 242 picometers is greater than 194. The correct answer cannot be C or D because 120 is less than 194. So I'm going to eliminate choices C and D. And now on to the first ionization energy. Let's take a look at the electron configuration for potassium and calcium. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and then finally 4s1 for potassium or 4s2 for calcium. So the valence electrons for both potassium and calcium are located in the same energy level, a 4s orbital or level 4. Potassium has 19 protons and calcium has 20 protons. And since calcium has a greater nuclear charge than potassium, there is a stronger attraction between the nucleus and the valence electrons. So it requires more energy to remove a valence electron from a calcium atom than it does to remove a valence electron from a potassium atom. So we expect the first ionization energy for potassium to be less than that of calcium, so less than 590 kilojoules per mole. So that makes B the correct answer to this question because 419 is less than 590. Now, let's take a look at question 2. It says, which of the following correctly identifies which has the higher first ionization energy, chlorine, Cl, or argon, Ar, and supplies the best justification? So I'm going to show you that same diagram that I showed you for question 1, but this time, instead of talking about the trend in atomic radius, I'll show you the trend for the first ionization energy. So the ionization energy value generally increases from left to right across a period, and the ionization energy value generally decreases from top to bottom down a group. And we know that chlorine and argon are located in the same period. So whoever has the higher first ionization energy value comes from that horizontal trend in which the ionization energy values generally increase from left to right across a period. So argon should have a higher first ionization energy than chlorine. That means that I can eliminate choices A and B. So I know that it's argon, but now I have to supply the best justification. So is it about the completely filled valence shell, or is it about a higher effective nuclear charge? So the explanation in question 2 is pretty much the same explanation that I already gave in question 1. When I was comparing potassium and calcium, I looked at the electron configuration. Let's go ahead and look at the electron configuration for chlorine and argon. So for chlorine, with its 17 electrons, that would be neon and then 3s2, 3p5. And argon, with its 18 electrons, it would be neon and then 3s2, 3p6. So we can see that the valence electrons in both chlorine and argon are located in the same energy level, which is level 3. Chlorine has 17 protons, and argon has 18 protons. So since argon has a greater nuclear charge than chlorine, there's a stronger attraction between the nucleus and the valence electrons. It requires more energy to remove a valence electron from an argon atom than it does to remove a valence electron from a chlorine atom. So the correct justification is not the completely filled valence shell, it is a higher effective nuclear charge. So correct answer is D. Now let's take a look at question 3. It says, which of the following correctly compares periodic properties of two elements and provides an accurate explanation for that difference? In choices A and B, we're focusing on first ionization energy. Let's take a look at the periodic trends for ionization energy. And so the trend is that in general, from left to right across a period, the ionization energy values increase, and from top to bottom down a group, the ionization energy values decrease. So the first two elements that we're going to compare are what are listed in choice A of this question, and that is the elements carbon and silicon. So based on this trend for ionization energy, we would expect the ionization energy of silicon to be less than that of carbon. Now let's see what it says in choice A. In choice A, it says the first ionization energy of silicon is greater than that of carbon. We know that's incorrect, so we can eliminate choice A. Now on to choice B, we're comparing chlorine and sulfur. Chlorine and sulfur are in the same period, and since ionization energy values generally increase from left to right across a period, we would expect the ionization energy of chlorine to be greater than that of sulfur. Let's see what it says in choice B. It says the first ionization energy of chlorine is greater than that of sulfur, so at the moment, we cannot eliminate choice B just yet. Let's take a look at choices C and D, and now we're talking about the trend in atomic radius. So for atomic radius, that generally decreases from left to right across a period, and atomic radius generally increases from top to bottom down a group. Let's compare the elements chlorine and bromine, which are in the same group. We would expect the atomic radius of bromine to be larger than that of chlorine. Let's see what it says in choice C. It says the atomic radius of bromine is larger than that of chlorine, so that's correct. Let's skip the explanation for the moment and take a look at choice D. We're comparing calcium and magnesium. So here are calcium and magnesium. They're in the same group. We would expect the atomic radius of calcium to be larger than that of magnesium. In choice D, it says the atomic radius of calcium is smaller than that of magnesium. We know that's incorrect, so we can eliminate choice D. Now, we've narrowed down our answer to either B or C. Let's take a look at the explanation and see which one is accurate. In choice B, it talks about comparing the electronegativity of sulfur and chlorine. So when I had presented in topic 1.7, which is on periodic trends, the trend in electronegativity, you can see on this slide, here is the general trend that electronegativity values tend to increase from left to right across a period, and they tend to decrease from top to bottom down a group. So there are the elements sulfur and chlorine. So based on this trend, we would expect sulfur to have a lower electronegativity value than chlorine. But in choice B, it says that sulfur has a higher electronegativity than chlorine. That is incorrect, so we can eliminate choice B. Now let's take a look at the electron configurations of bromine and chlorine and see why this explanation is accurate. So the electron configuration of chlorine would be neon, 3s2, 3p5. The electron configuration of bromine would be argon, 4s2, 3d10, 4p5. Let's focus on the electron shell. So we have level 3 for chlorine for the valence shell, and we have level 4 for bromine for its valence shell. And so the reason why choice C is correct in terms of its explanation is that, yes, as you can see here, bromine has one more occupied electron shell, which increases the distance between the valence electrons and the nucleus. So that's why the atomic radius of bromine is larger than that of chlorine. So correct answer to question 3 is C. Now let's take a look at question 4. We are given a table for the elements boron, carbon, nitrogen, oxygen, fluorine, and neon, and they are all located in period 2 on the periodic table, with data for first ionization energy and atomic radius. So question 4 says, the table above shows the first ionization energy and atomic radius of several elements. Which of the following best helps to explain the deviation of the first ionization energy of oxygen from the overall trend? So the overall trend in general for ionization energy is that as you move from left to right across a period, we expect the ionization energy values of the elements to increase. So from boron to carbon to nitrogen to oxygen, take a look at the data in the table. For boron, it's 801 kilojoules per mole. For carbon, it's 1,086 kilojoules per mole, so that's higher. For nitrogen, it's 1,400 kilojoules per mole. Again, that's higher. But then right there in the table, we can see that the first ionization energy for oxygen is actually less than that of nitrogen. So the message here is that for some reason, removing the first electron from the valence shell of oxygen is slightly easier than removing the first electron from the valence shell of nitrogen. So why is this? Well, back when I was teaching topic 1.7, which is periodic trends, I had presented some anomalies in the horizontal trend for first ionization energy, and this is one of the anomalies. You can see on this slide, I'm highlighting the fact that the first ionization energy of oxygen is slightly less than that of nitrogen. So here is the explanation. Although oxygen has one more proton than nitrogen, the ionization energy of oxygen is slightly less than that of nitrogen. This decrease in ionization energy can be explained as follows. There is slightly more electron-electron repulsion between the paired electrons in the p4 configuration of oxygen as compared with the p3 configuration of nitrogen. This electron repulsion in the p4 configuration explains why it requires slightly less energy to remove an electron from an atom of oxygen than it does to remove an electron from an atom of nitrogen. So we're looking for electron-electron repulsion, and you can see in our choices that in choice C, that's exactly the correct explanation. There is repulsion between paired electrons in oxygen's 2p orbitals. So correct answer to question 4 is C. Now let's take a look at question 5. In question 5, we are given a table with ionization energy values in units of kilojoules per mole, and they are labeled as first, second, third, fourth, and fifth. So question 5 says, the first 5 ionization energies of a second period element are listed in the table above. Which of the following correctly identifies the element and best explains the data in the table? So the answer choices for the identity of the element, it's either boron, B, or nitrogen, N. What I'm showing you on this slide is something I had presented when I was teaching about topic 1.7, periodic trends. And what you can see is a table with successive ionization energy data. So first ionization energy, second ionization energy, third, and so forth and so on. Now, highlighted in yellow in this table are the electrons in the outer shell, or the valence electrons. And then highlighted in gray with that red outline, those would be the inner shell, or the core electrons. And so as you can see, the ionization energy values, they generally increase every time another electron is removed. But when there is a significant increase in the ionization energy value, that tells you that you are removing an inner shell core electron, which is much closer to the nucleus and requires much more energy to remove. So what you're looking for is a significant increase in the ionization energy value to tell you that at that point you've removed all of the valence electrons from that atom. Now let's go back and take a look at the data in the table for question 5. So first ionization energy, 801. Second ionization energy, 2,430. So that's a higher value, but not a significant increase. Third ionization energy, 3,660. Again, higher than the second, but not a significant increase. And now we come to the fourth ionization energy. That's 25,000 kilojoules per mole. So that tells us that we have now removed all of the valence electrons, and it requires much more energy to remove those inner shell core electrons that are much closer to the nucleus, much harder to remove. So the conclusion from this data in the table is that this element has 3 valence electrons. Now let's take a look at the electron configuration for boron and nitrogen. So for boron, it's 1s2, 2s2, 2p1. So as you can see, we have 3 valence electrons for boron. And for nitrogen, it's 1s2, 2s2, 2p3. We have a total of 5 valence electrons for nitrogen. And we are looking for an element that has 3 valence electrons. So the correct answer to question 5 is B. The identity of the element is boron because the data in this table tells us that this element has 3 valence electrons. Now, let's take a look at question 6. In question 6, we have a data table with successive ionization energy values. So this data table is very similar to the data table that was presented in question 5. And like question 5, what we're looking for is that significant increase in the ionization energy value, which will help us to determine how many valence electrons there are for this element. So in question 6, it says, based on the ionization energies of element X given in the table above, which of the following is most likely to be the empirical formula of an oxide of element X? So the first ionization energy of element X is 738 kilojoules per mole. The second ionization energy is 1,451 kilojoules per mole. And while that's higher than the first ionization energy, it's not a significant increase in that value. And when we get to the third ionization energy, now that is a significant increase in the ionization energy. It's 7,733. So based on that pattern of data, we know that element X has 2 valence electrons, because when we get to the third ionization energy, that is such a significant increase in the ionization energy value, it means that now we are removing an inner shell core electron, which is much closer to the nucleus and much more difficult to remove. So now that we know that element X has 2 valence electrons, let's take a look at this pattern, which I had presented when I was teaching topic 1.8, which is valence electrons and ionic compounds. You'll notice that 2 valence electrons would be an element located in group 2 of the periodic table. And for element X, if it has 2 valence electrons, it is likely to form a monoatomic ion with a charge of +2. And if it forms an oxide, that means it's reacting with oxygen. Oxygen is in group 16. It has 6 valence electrons, and oxygen normally forms a monoatomic ion with a charge of -2. So when element X and oxygen form an ionic compound, the +2 charge and the -2 charge exactly cancel each other out. They balance each other to form an overall charge of 0. So the empirical formula of an oxide of element X is likely to be XO. And that makes the correct answer to question 6, choice A. Now let's take a look at question 7. In question 7, we are given two balanced chemical equations. The first equation involves potassium reacting with water to produce the ionic compound potassium hydroxide and hydrogen gas. The second equation involves calcium reacting with water to produce the ionic compound calcium hydroxide and hydrogen gas. So in question 7, it says both potassium and calcium react with water according to the equations shown above. Which of the following identifies the element that reacts more vigorously with water and provides the correct justification? Let's take a closer look at what happens to potassium and calcium when they react with water. So potassium reacts with water to produce the ionic compound potassium hydroxide, which contains potassium ions, K+, and hydroxide ions, OH-. It also produces hydrogen gas, H2. When this equation is balanced, the coefficients from left to right are 2, 2, 2, and 1. So as we balance this equation, we're going to add another water molecule to the left. So now the oxygen atoms are balanced. We're going to add another formula unit of potassium hydroxide to the right of the equation. So now the hydrogens are balanced. And then we'll add a potassium to the left. And now the entire equation is balanced with coefficients of 2, 2, 2, and 1. When calcium reacts with water, it produces the ionic compound calcium hydroxide, which contains calcium ions and hydroxide ions, and it also produces hydrogen gas. And when this equation is balanced, we'll add another water molecule to the left. Now we have coefficients from left to right of 1, 2, 1, and 1. Look on the right side of the equation, you'll notice that K has a positive 1 charge and Ca has a positive 2 charge. So when potassium and calcium react with water, they are losing electrons to become positive ions. And so the process of losing electrons is related to the concept of ionization energy. Let's take a look at the periodic trends for ionization energy. Here we see potassium and calcium are in the same period, and ionization energy generally increases from left to right across a period. So from this trend, we know that potassium should have a lower ionization energy than calcium. And if the ionization energy of potassium is less than that of calcium, that means that potassium loses electrons more easily than calcium does. So when they react with water, we expect potassium to be more reactive than calcium with water because potassium loses electrons more easily. It has a lower ionization energy. Now let's take a look at the 4 choices we are given in question 7. Since we know that potassium should react more vigorously with water, then the correct answer is either A or B, and it's because of that lower value for the first ionization energy. So the justification is what we see in choice A. And the reason why the justification in choice B is incorrect is because based on Coulomb's law, we would expect a higher magnitude of charge to have a greater attraction for a water molecule. So therefore, the calcium 2+ ion would actually have a stronger attraction to the water molecules than the K+, because it has a greater magnitude of charge. So the justification in choice B is actually incorrect. So the correct answer for number 7 is A. Potassium is going to react more vigorously with water than calcium because the first ionization energy of potassium is less than that of calcium. It means that potassium loses electrons more easily than calcium does. Now let's take a look at question 8. In question 8, it says properties of the compound CaCl2, or calcium chloride, are listed in the table above. On the basis of periodic properties, which of the following compounds should have properties that are most similar to those of calcium chloride, or CaCl2? So all 4 choices contain chloride, or Cl, but in choice A, we have sulfur. In choice B, we have barium. In choice C, we have boron. And in choice D, we have carbon. And if we look at one of the essential knowledge statements in topic 1.8, valence electrons and ionic compounds, it says that elements in the same column or the same group of the periodic table tend to form analogous compounds. That means compounds that have similar chemical formula and properties. So since we have calcium chloride, let's take a look at an element that is located in the same group or the same column as calcium. And since barium is located in the same column or the same group as calcium, that makes choice B, barium chloride, BaCl2, the compound that is most likely to have properties that are similar to those of calcium chloride. So the correct answer for question 8 is B. Now let's take a look at question 9. Question 9 says, based on the positions of elements in the periodic table, which of the following pairs contains compounds that are most likely to have similar chemical properties? So the process of choosing the correct answer for question 9 is very similar to the process we used in question 8. We're looking for elements in the same column of the periodic table that tend to form analogous compounds. Let's start with choice A. So in choice A, we have selenium and titanium, and they're both bonded with oxygen. But since selenium and titanium are not in the same column of the periodic table, it is unlikely that choice A is the correct answer. In choice B, we have calcium that is bonded to either carbon or fluorine. But since carbon and fluorine are not located in the same column of the periodic table, it is unlikely that choice B is the correct answer. In choice C, we have magnesium, and it's bonded to either chlorine or bromine. And since chlorine and bromine are located in the same column or the same group of the periodic table, then that choice C, is likely to be the correct answer. And let's take a look at choice D. We have scandium and phosphorus, and they're both bonded to chlorine. But since scandium and phosphorus are not located in the same column of the periodic table, it is unlikely that choice D is the correct answer. So the correct answer for question 9 is choice C. And so magnesium chloride and magnesium bromide should have similar chemical properties because chlorine and bromine are located in the same column of the periodic table and would tend to form analogous compounds with similar chemical properties. All right, well, question 9 was the last question in this packet. I hope that you found all of the answers and explanations helpful. Thanks for watching.